Alrighty, so welcome back. We are now going to be talking about one of the most common and powerful uses of neural networks, and that is for image recognition. This is typically what people think of when they think of neural networks, is for image recognition. So it seems like it would be incredibly complicated, but it's actually not that bad. Convolutional neural networks are pretty cool. So here we go. Um, if you think back to the video that um, you watched at the beginning of the neural networks, where it was describing a neural network that could tell the difference between individual digits, like the numbers 0 through 9. That's what we're talking about here. A network that can uh, take in an input and then classify that input into categories. So think of it as a logistic regression that is works on images. So it's way more interesting than logistic regression, though. Alrighty, so we're going to start this off with a simple example, and I'm going to pause and make the matrix so that you don't have to watch this in detail, and then it'll just magically be there as we resume. Alrighty, and so we are back, and a beautiful 6 by 6 matrix has appeared so that you don't have to watch me write all that down, which is painful to say the least. So this is a 6 by 6. And then we're going to have a 3 by 3 right here. And we're going to fill it in with values that seem a little bit strange. Going down the columns, 1, 1, 1, 0, 0, 0, -1, -1, -1. Okay, this is a 3 by 3 filter. Okay, and we're going to convolve it with the original matrix. This is the convolution operator. And you've probably seen this in some of the more advanced mathematics classes you've had them. The convolution operator. Take two things and do something with them. Alrighty, so that is the operator, and this is going to yield, when we're done, a 4 by 4 matrix at the end. Let me get that ready to go. All right, almost there. All right, not too bad. So this is a 4 by 4. Now, this is how it's set up. We're going to start with this as our sample example, and let's see what we get. So what we're going to do is we're going to take the 3 by 3 filter and kind of overlay it on top of the 6 by 6 matrix, and then perform some mathematical operations. So in this case, all we're going to do is take the value that is in the filter and multiply it by whatever value is underneath it once we place the filter on top of the 6 by 6 matrix. So we're going to start off with, let me get my color here, change this to green. We're going to take the 3 by 3 and we're going to overlay it on top of this 3 by 3 set of values in our matrix over here. Alrighty, and what we're going to do is every number gets multiplied by whatever the filter number is that's on top of it, and added together as we go. So this one would be 2 times 1 plus 0 times 4 plus 1 times -1 plus, so that's the first set. If I picked these parts of the filter right here and overlaid it where it's a 1 here, a 0 here, a -1 here, that's how we got these values. And now the center row is going to be on the center row right here. So this is going to be 1 times 1 plus 3 times, oops, I think I did it backwards, didn't I? I don't know why I did the 4, 0 times 4 there. That should be, let me change that to where it's not. Wow, that's very large. Eraser. Let me try that again. That should be 4 times 0 plus, there we go. I want to keep the values times the operation. So it sticks to the right order. 1 times 1, 3 times 0, plus 8 times -1. And then we move down to the last row. So plus 5 times 1, plus 7 times 0, plus 6 times -1. Alrighty. Now, let me see what we get here. So if 2 times 1 is 2, 4 times 0 is 0, 1 times -1 is -1, 1 times 1 is +1, 0, -8, 5, 0, and -6. That's a 5. Alrighty. So if I add all these together, I get 2 plus 0 plus -1. It's going to give me a +1. Plus 1 is 2. Minus 8 is -6. Plus 5 is -1. Plus -6 is -7. So this should be a -7 that gets entered into our resultant matrix over here, our 4x4. Okay? So what I also want to point out before we do the next one is these values as we go down the columns of our 3x3 filter are the same. So I could do something that looks like this based on math. 2 plus 1 plus 5 times 1 plus 4 plus 3 plus 7 times 0 plus 1 plus 8 plus 6 times -1. Right, I just reordered this into a much more compact and easy to read thing. So this would give me 8, 0, and then this would be, what is that, -15, -15. And so we get -7 if we add these together. So I'm going to do it this way for the next one, just because this is more compact and less chance of error. So let me erase this. Reduce the size a little bit. So here we go. So the next thing we're going to do, now that we've completed the first convolution, is we're going to shift the filter over 1. So the next one, let's use orange. Let's go with this set of values right here. Okay, so that one is going to be, using the new method, 4 plus 3 plus 7 times 1 plus, we're going to have 1 plus 8 plus 6 times 0 plus 0 plus 9 plus 0 times -1. Well, what does this give us? Well, let's see, this gives us 14, 0, and -9. So I get a +5 over here. Okay, let's do another one. That's a lot easier, right? Yeah, that's a much, much easier way of doing that. Alrighty, so now let's go with light blue. And we'll be looking at this set of values right here as we move the filter over by 1 place to the right. So now we're going to have 1 plus 8 plus 6 times 1 plus 0 plus 9 plus 0 times 0 plus 1 plus 4 plus 3 times -1. So this gives me, what is that, 15, 0, and 8, -8. So that is a positive 7 over here. Alrighty. Now, if I repeat this process, go to a different color, I would move it one step to the right. So it would look, it would be right over here, just like this. And when I did all those values, I would wind up with something that looks like -2, I believe, just looking at it. Okay, now I've convolved the filter with the pixels heading straight across, but now I've reached the edge. What do I do next? So what I do is I go back to the beginning and shift down one and then repeat the process. So you can think of that as the next set of pixels are going to be these in red. So what is that going to be? 1 plus 5 plus 8 is 14. -9? Yeah, I got -9 for that. So you continue shifting over by 1 pixel at a time, doing your convolution with your 3x3 filter on each block until you get down to the very end, and then you will have filled out your 4x4 matrix over here, your resultant matrix. Alrighty? So, not too bad, right? Not too bad at all. So, at least I don't think it's too bad. I kind of like that. Now, I'm going to, let's see, do I want to do that? Yeah, I'll do it that way. I'm going to pause again and redraw the matrix with different values. So here we go. We're going to pause and you'll see something new in just a sec. Alrighty, so we are now back with a new 6x6. And in this case, we're going to be talking about what these numbers actually mean. The numbers are going to represent brightness levels, where a 9 represents a pixel that is fully bright, it's white, it's a white pixel, and a 0 represents a fully dark or a black pixel. So what we're going to have is all of these are going to be white pixels, and all of these over here are going to be black pixels. Okay? So we have a group, an area that's all white, and a group area that's all black pixels. So what happens now when we run this convolution operator, or rather the filter using the convolution operator onto our matrix? What do we get? Well, we get something that looks a little strange. If I put this over on this, I'll again highlight, it's going to start right here, right? Well, when I add it all up, I'm going to have 27 plus 0 plus -27, which is going to be 0. Positive 27 plus -27 plus 0 is a 0. Okay, now I'm going to shift it. So I'm going to shift it over here. What do I get then? Well, I'm going to get 27 plus 0 plus 0. I get a positive 27. Okay, shift it over again. Now it's going to be over here. What do I get? 27 plus 0 plus 0, 27. And then I shift it over again to right here. And I'll wind up with 0 plus 0 plus 0, and that's a 0. So far so good. Let's now shift it down one more. Let's come back over here, and yeah, you can already see what's going to happen. The values are going to repeat themselves because it's the same values as you go down this 6x6 matrix. So we're going to wind up with a 0, and then the rest of them just get filled in the same way. 27, 27, 0, 0, 27, 27, 0, 0, 27, 27, 0. Alrighty, so what happens here? Well, when we ran this filter across this image, where these are the pixel intensities, we wound up with a large positive value setting up inside of the middle of our resultant matrix, our 4 by 4. Um, that's odd. Not really, it makes perfect sense, but why is it we have zeros on the sides and we have large positive values in the middle? The reason is this is called a vertical edge filter, because if there is a vertical edge that transitions between light and dark or dark to light, you're going to wind up with, at the point of transition, large values. I'll just say that for now. The reason I wanted to be careful with how I say that is, what happens if I switch the order? What if I put all the black pixels over on this side and all the white pixels on this side? Well, let me pause and do just that, and we'll see what happens. Actually, you know what? I'm just going to make that right down here. That way I don't have to. Here, I will pause though, but I'm going to draw it at the bottom so I don't have to redraw all of this. So, pausing one more time. Okay, so now that I've redrawn this, we have a different situation. Now, on the left side, we have the black pixels, and on the right side, we have the white pixels. Okay, so now when we convolve it, we're going to start off convolving with this set right here. What do we get? Same filter. The filter has not changed. It's still 1, 1, 1, 0, 0, 0, negative 1, negative 1, negative 1. Well, we get, again, a 0 here. Then we move over by 1. When we do that, we get this set of pixels. Okay. I get a 0 plus 0 plus negative 27. So this winds up being a negative 27. Then I repeat the process. Now I'm looking at this set of pixels. When I do that, I get a 0, and again a negative 27. And then finally I move over to the last one, right here. And this set I get 27 plus 0 plus negative 27 back to 0. And you can see that I'm going to wind up filling it in exactly the same as I did for the very first row. Now the difference is that instead of positive 27s, I have negative 27s in the center of my 4x4. So I'm going to let that sink in. What changed? Right. A single vertical edge filter can not only detect that there is an edge, a transition, it can tell whether it's transitioning from light to dark or dark to light based on the values. If they're a large positive value, it's transitioning from white to black. If it is a large negative value, it's transitioning from black to white. So I hope you're as impressed by that as I was the first time I saw it. That's stunning. All of that from just running a 3x3 filter with these columns of values across our pixel values. We're able to detect vertical edges this way, which is absolutely amazing. Just stunning. Couldn't be more impressive. Alrighty. So, now that we have gone through that, let's move on to something, just a slight change, and see what happens. I think I can get by with it by, yeah, I'm going to do that. Let me go to to the next slide and change this filter in the middle. So if I change the filter, do this, erase. This is pure skill right here. Oh man, that worked out way better than I was expecting it to. I thought that was going to fail. Alrighty, so what if I change it to, instead of 111 going down, what if I put 111 horizontally, 0, 0, 0, -1, -1, -1. Right. At that point, I no longer have a vertical edge filter. I have a horizontal edge filter. So based on how I set my values within my filter, it tells me different bits of information about my image. And I could even set it up where there were diagonal values, 3, 1, 1, 0, 0, 0, -1, -1, -3, for example, and it would detect diagonal edges. So that's how you can use extremely simple filters to pull out actual physical information about your image. What's actually happening, the edges, the transitions, all from math. Um, it doesn't have to know anything about what the image is. It just uses straight math to convolve a filter with the pixel intensities, and then it analyzes what it gets as a result. I hope that's as impressive to you as it was to me. Alrighty, so that's how the convolutional neural networks work in essence. And I should also say that the filter values are where your parameters are going to be stored. So as it makes its guesses and then it goes backwards and adjusts the values, it adjusts the values of the filters in order to um, figure out what an image is. If we're talking about the digits, if it's is it a 1 or a 9 or a 7 or whatever. So moving forward from there, we have a couple of problems that we start to run into. So let me go to the next slide. This one is actually, it's not an obvious problem until you really see it. So again, I'm going to pause for just a second and set up my um, matrices a little bit differently. Okay, so be right back. Okay, and we are back. So here's where one of the problems comes in with doing these filters and using for the convolutional neural network. Uh, you start running into some issues with how many times a pixel is actually counted, how many times it's interacted with by the filter. And this is a nice clear example of that because if I look at the number of times that x1 is interacted with, well, when I place my filter over and then I start moving it across, down, etc., how many times does the value at x1 get interacted with? Just once. One time only. Right? The very first time I put it down, it hits that corner and then it never gets touched again. What about x2? How many times does that get touched? X2 gets touched. It gets interacted with 3 times because it gets touched when it's in this corner, then when it's right here, and then finally right here. And then it will shift down and it will never interact with this particular pixel. Say that 3 times fast again. What about x sub 3? How many times does that get interacted with? That gets interacted with 9 times. So that is the maximum number of times that a pixel will be interacted with a 3x3. Every time that filter is moved, it interacts with a different one of the positions on the filter that pixel does. So we can see a problem. The edges, the sides of our image are not being counted as much as the pixels that are in the middle. So what this can do is it can give more weight to the middle pixels than to the edge pixels, and especially the corner pixels. So to combat that, we do something that's called padding. This is a very common thing to do in machine learning, is padding. So what we're going to do is we're going to add rows and columns of zeros to our original matrix. Okay, so let me do that. You bear with me. I'm not going to disappear for this one. Oh, I'm going to have to get rid of this 6 by 6 down here. All right, bear with me. Here we go. I'm just adding additional columns and rows. Okay. Now, inside the padded cells, the extra cells, I put zeros. Why am I putting zeros here? Let me rephrase that. I put a neutral value here, okay? It, you would not put black pixels here, or you can if you want to, but you could put a gray pixel, you could put a white pixel, but typically you'd want something that isn't going to affect too much. But black is used. We can say that. That's fine. Alrighty. Now that we have padded the outside of our original matrix, our original image with these zeros, how many times is X1 interacted with? Well, now X1 is interacted with how many times? Survey says, well, when I initially place it here, it will be at the center location, so it'll be 1 time, 2 times, and then it will come back and shift down 3 times, 4 times. So now it's going to be interacted with 4 times. Okay. What about X2? Now X2 is going to be interacted with 6 times. And you can already see why we do this. By adding the padding, we help preserve the impact of the pixels that are at the edges and corners of our image. It actually will detect them and use them more than if we don't have padding. The other thing that padding does, which you'll see it used for quite a bit, is the result now is not going to be a 4 by 4. The result is actually going to be, let me erase this here. It is actually can you guess? Yeah. All right, so see how horribly I can do this. It goes from a 4 by 4 to a 6 by 6. So what happened? We started with a 6 by 6. We added padding to the 6 by 6, and the result was a 6 by 6. So padding can not only be used to give more impact to the corner and edge pixels on your image, it can be used to preserve the size of your matrix. You start off with a 6 by 6, you end up with a 6 by 6. So that's what padding can do for you. Alrighty? Now, let me clear this and let's talk about the very last things for convolutional neural networks. So we'll go to the next slide. Let's see, I've talked about that. And now this. Here we go. So for, oh, forgot to clear the screen. Clear this. I know I can clear it, I promise. Alrighty. There are 2 other common operations that are performed on convolutional neural networks. Okay, one of them is called striding. So striding. Okay, so striding. I'm not going to draw this in a lot of detail because it's not really all that interesting. Um, striding is what you would use if you wanted to move your filter in step sizes larger than one. Okay. Well, for example, I almost forgot I've got to do a 7x7, not a 6x6 for this example. Otherwise, it won't come out evenly. I know. This is why I was pausing y'all, so y'all didn't have to suffer through this. 7x7 right here. If I do a striding of 2, so a striding of 2, stride equals 2, here's what it's going to look like. And this is with a 3x3 filter. It's going to start here, but it's not going to move 1 pixel over, it's going to move 2 pixels over when it's done. So the next one is right here. And then the next one is located right here. So this is assuming we have a 3x3 filter. You can already tell that because that's what we're overlaying on top. With a 3x3. What's the resultant matrix look like? What are its dimensions? We're striding 2. Yeah, it winds up as a 3x3. So striding is used to greatly reduce the size of your next matrix. Um, so when you're going through the layers of your neural network, one layer might be looking for vertical edges. The next layer might look for combinations of vertical edges or horizontal. It's impossible to tell once it starts doing back propagation and adjusting all the thetas what it's really doing. But as it does all of these operations, as it performs all of these, it is going to come up with the best way that it can make a guess possible. Now, in at least in my brain, I can't imagine a stride of 2 working. It seems like you would be missing too much information as you did your striding. You would be going from a 7x7 to a 3x3, which is incredibly drastic. But it turns out striding is actually fairly useful in a lot of image situations. It will reduce the dimensionality, which reduces computational time, and a lot of times that is all we need. It still has enough information to be able to correctly identify images. So even though intuitively striding seemed like it would be a bad idea in order to preserve what the image actually is, what it looks like, what the features are in your resultant matrix, it actually works out fairly nicely. But a much more common method is called pooling. Now, pooling, I really enjoy pooling. This is a good one. So, pooling. There are 2 forms of pooling. Okay, I'm going to make a 4x4 right here, and a 4x4 I can populate and not feel too bad about y'all having to suffer watching me draw this and fill in with values. All right, so 7, 1, 1, 0, 2, 3, 4, 9, 2, 5, 1, 3, and 6, 3, 4, 1. I picked these out of thin air, so they're just some random values. Alrighty. Now, pooling, let's say we use a 2x2 filter. Okay. This is a 2x2 filter. If it is something called average pooling, let's see, equals, we'll do like this, average pooling, okay? We're going to wind up with a 2 by 2 as our result. And what it gives you is the average of the four values that the filter is on top of. So it would start off right over here. If I can find it, there we go. And it would look at those four values. So the average of those four, let's see, that's 7 plus 3 is 10, plus 3 is 13. 13 divided by 4 is 3.25, I think so. So that's 3.25. 3.25. So that's what gets put over here. Then it comes over to the next set of values. It completely skips over, so it's going to be this set of values now. And it finds the average of those values. That's 10, 14, that's going to be 3.5, right? And then likewise, if we come down here, this one is going to be, what, 7 plus 9, 16, so that's going to be 4 even. And last but not least, for these bottom four, we have 2 plus 7 is 9 divided by 4. What is that? 2.2, 2.25, something like that. All right. So that's average pooling. The other type of pooling is called max pooling. Okay. Now max pooling just looks at the four numbers and it copies over the largest one. So out of this initial block here, the 7 is the largest. This block, the 9 is the largest. This block down here, the 6 is the largest. And over here, the 4 is the largest. Now, which one of the poolings typically is more useful with image recognition? You probably already tell I'm asking that for a reason. It turns out max pooling is what's typically used for image recognition. Here's why. Max pooling maintains the intensity of the features, the largest intensity. So it finds out of a little area inside your image what the largest intensity pixel value is. Average pooling averages all those values. So what an average pooling winds up doing is it blends all of the intensities together into kind of a blurred mess. The average pooling doesn't preserve the features as well as the max pooling usually. So max pooling is computationally less intensive than average, and it's typically what you're going to see for your image recognition. Max pooling is used all the time because it reduces the dimensionality of your original matrix while preserving some of the information about the intensity levels within those little sub areas. So this is an extremely common way of reducing the dimensionality of an image is through max pooling. Average pooling, not so much. You lose so much information when you do the average pooling. So max is the one that wins almost all the time. Alrighty, that is convolutional neural network in a nutshell. We'll be going over the code next time, and hopefully you will enjoy actually seeing some image recognition. So I look forward to it. Y'all have a wonderful rest of the day, and I will see you later. Bye, everyone.